Section 2.3, functions and their graphs. The first thing we're going to look at is, what is a function? Well, in order for something to be a function, for every one input, there can be only exactly one, and only one, output. So for our purposes, each x coordinate can only have one y coordinate assigned to it. Okay? So this is just a formal definition of a function, but as long as you understand that for every x value you can only have one and only one y value, then you have what's called a function. And we'll be looking at, the function notation and the domain and range of a function as we progress through this section. Okay? So function notation is this. This is actually, Lagrange came up with this, and then Leibniz is the y equal to way of notating it. But if you see something like this, this means f with x in its domain. And this is always going to be equal to some expression in terms of x. All right? Another way to look at it is this function f with x in its domain really is implying the value of the function f at x. All right? So there, of course, is an awful lot we could discuss regarding functions. We can go into a whole lot of depth. But again, as long as you understand the material that I'm presenting to you via YouTube and also the in-class exercises we look at throughout the week, you should be good to go on the tests in this course. Okay, so let's look at our first example. We're going to let the function f be equal to 10 minus 3x squared, and we're going to be finding the following. So in the first one, it says f of negative 4. So what this means is, this is function notation. What this means is we're now going to replace every x in our original function, and in this expression, with a negative 4. So what that looks like is 10 minus 3, and then wherever you see an x, replace it with a negative 4, use parentheses, and then if possible, you simplify this. So what will we get here? Well, you can just use a calculator. That's probably the best way of doing it. Or you can just go through the motion. So 4 squared, 16. And then you do what? You do 10 minus what? 3 times 16. You got to do multiplication first. That is a 48. And then ultimately 10 minus 48 is negative what? 38. So f of negative 4 is exactly the same as negative 38. So what this really means is that when x is equal to negative 4, the corresponding y coordinate is negative 38. It's an actual ordered pair, a point, on the graph of this quadratic function. All right, what about letter B? F of x minus 1. Okay, well, what does that mean? Well, again, it means the same thing. Wherever you see an x in your original function, you replace it with whatever is inside of these parentheses. So you get this. So the first part of this is, of course, to rewrite it correctly. And then let's make sure we can simplify this correctly. So x minus 1 squared means what? It means you have x minus 1 times x minus 1. So that gives us this trinomial. X squared minus 2x plus 1. And then you distribute the 3 through, the negative 3 through, you distribute the negative 3 through, and you get a negative 3x squared plus 6x minus 3, and then combine like terms if possible. So it is possible to do so here. And so your final answer is negative 3x squared plus 6x plus 7. All right. This one actually is a component of what will be called the difference quotient. And then in calculus, it'll be called the definition of the first derivative. So this is a pretty critical piece right here in terms of understanding how to work with it using function notation. So let's see what we can do. Well, it's the same thing. Wherever we see an x, we replace it with whatever this is. All right, so what do we get here? This binomial squared, quantity a plus h times quantity a plus h gives us a squared plus 2ah, 2a plus h squared, which will ultimately give us this. (10 minus 3a squared minus 6ah minus 3h. Again, this is going to be critical. You know how to work with this function notation, this one specifically, because it'll be part of the difference quotient, and ultimately, in calculus, a part of the definition of the first derivative. All right, the next example deals with what is called a piecewise function, because this function f consists of two or more pieces, okay? Each piece is defined by an expression in terms of x, and also a restriction with respect to the domain of x. So this expression, 3x minus 4, only exists, only is true, if the value of x is less than 0, so if x is negative. This piece, 3x plus 1, only exists when x is greater than or equal to 0. Okay, so let's evaluate this function when x, first of all, is negative 2. So we'd write down f of negative 2. We're evaluating this function at this x value, negative 2. Well, in order to do this correctly, you have to look first at the restrictions. This is the one we're going to use. Why? Because x is less than negative, excuse me, x is less than 0, and we're looking at evaluating it at negative 2. Negative 2 is less than 0. So we're only using this first piece. So that would be 3 times the quantity of negative 2 minus 4, which is equal to what? Negative 6 minus 4, so negative 10. So the value of this function when x is negative 2 is based on this first piece, because this only exists when x is less than 0. Negative 2 is less than 0. That's why we're using this. All you got to do is substitute negative 2 in for this x and only this x, and you get your negative 10. That's it. You don't plug it in this one. That wouldn't make any sense. Then you're not looking at a function anymore. Remember, for each input, you have exactly one and only one output. All right, so f of 0. F of 0, which one do we use? Well, we got to use this one, because this is in existence when... Whoa, wow. Excuse me. All right. Let's continue. This only exists when x is greater than or equal to 0. So we're using the second piece, 3 times substitute in the 0, and you just get 1. That's it. And then an f of 2, well, is 2 greater than 0? It sure is. So we're going to use the second piece again. So 3 times 2 plus 1, 6 plus 1, 6 plus 1 is 7. And we're finished. All right, one thing we can do when we're trying to determine whether or not a graph is that of a function is we can use what's called the vertical line test. All right, so what that means is, what is the test all about? Well, here's what this is saying. If you can put a vertical line anywhere through the graph of whatever is in front of you, and this vertical line only intersects the graph at one and only one point, then the function is, yes, a function. So this is a function. Yes, this graph is that of a function because it passes the vertical line test. This one, however, it's a relation of points, but it's not a function because I can put my vertical line in this region, and guess what? It's intersecting the graph in 2 points, right? So in order for it to be a function, again, for every x value, like let's look at this x value, negative 2. For every x value, you can only have one and only one output. Well, this x value, negative 2, has 1 and 2 outputs. So it's not a function because that is the case. It's also, again, doing what? It's failing the vertical line test, not a function.